I'm only going to go through a few past paper questions that you can see how these questions are asked. Now, this was asked last year, and you will see that they have a small coil at rest connected to a sensitive voltmeter, which is situated near a stationary solenoid as shown. Now, I'm obviously emphasizing those words for a reason, because if they say a small coil at rest and the solenoid is stationary, you should immediately know that there's no change in the magnetic flux, and therefore there can be no induced EMF, no induced current. But the first one here states Faraday's law of electromagnetic induction. Now, please remember for this law, get it right. 2 marks. So it's going to be the EMF is directly proportional to the rate, and you have this equation on your information sheet, the rate of change in magnetic flux linkage. If you just said magnetic flux, it's also fine. Do not say equal, because remember it's not equal, because then we need the minus sign. Now, why has the voltmeter got a 0 reading? Now, this is the type of question that you can always expect. If there is no motion relative to each other, so the coil is not moving relative to the solenoid, and the solenoid is not moving relative to the coil, the coil and the solenoid is stationary. Therefore, there is no change in magnetic flux. So if this magnetic flux here is 0, the change in magnetic flux or magnetic flux linkage, then the EMF must be 0. So therefore, there will be no EMF induced in this small coil. And then the last question states 3 different ways in which an EMF now could be induced. Now you need to think about different ways. Not movement is one way. So if you said move this small, now remember there's already a current in this solenoid. So you can't say add a current, because there is a current flowing there. You need to say how you can get an EMF here. So you could move this small coil away or towards the solenoid, or you could move the solenoid away or towards the small coil. But that would be one way. If you were moving them away or towards each other, that would be, so keep on moving them. If they are moving, then there's a change in magnetic flux, and then there's an EMF induced. The other way you can do it is to rotate one of them. So you can say rotate this coil or rotate that coil. Then the last thing you can do is change this current. But you can't just say use a higher current or use a lower current. You have to say keep on changing this current, because if the current is changing, so that means there's a magnetic field forming, disappearing. Then there is a change in the magnetic flux again, and therefore there will be an EMF induced. So you need to think of 3 different ways in which you can create a change in the magnetic flux linkage and therefore induce an EMF. If you were going to talk about the windings, you need to say you need to constantly change the winding. So you can be taking the wire off or something like that, but you need to think about it changing. Just using more windings, if it's still stationary, is not going to be a change in the magnetic flux. You need to then constantly change the number of windings. So just be careful about how you answer these questions. The next one, here you have a magnetic flux graph. So it tells you that the magnetic flux is shown here. They ask you during which time interval will the induced EMF be positive and non-zero. Now remember, if you think about the EMF is equal to minus the change in magnetic flux linkage over the change in time. Now remember, if you look at the flux graph, this is the gradient and that's the negative. So this was just flux, it wasn't linkage, but remember that is just changed by the number of windings, so not that important. But the EMF is the negative gradient of the flux graph. It doesn't have to be a sine graph or a cos graph. Please remember that. not it's not always going to be a curve. So if we look at all the stages, I'm actually going to look at all the stages so that I can explain this to you nicely. So if you look at the flux graph here, the gradient here is negative and it is constant. So if the gradient is negative and it is constant, that means the EMF will be positive and constant. So if I was going to go and draw, and I'm going to do that here, I'm going to draw a whole EMF graph for you so that you can actually see what it would look like. I don't know why that plays funny buttons with me now. There we go. Come back line. And we want the EMF graph. There we go. So we have EMF here versus time. I'm going to draw it for all those intervals. So if we have A, B, C, D, and E. Now remember, they often ask you for sketch graphs, and you don't have to do this to scale. Now here we said the flux is decreasing, so that means the gradient of this flux graph is negative and constant. Constant because it's a straight line. The flux is decreasing, but the gradient is not decreasing. The gradient is constant. Straight line has a constant gradient. So I'm not going to draw a negative line here because of the negative there in the equation. It's going to be a positive line there. Constant. Sketch graph, so you don't need values. Here, the gradient is 0. Now I really need to use another color. So for this bit here, the gradient is 0. So that means my EMF will be 0. So you just draw a flat line there at 0. For the next bit, this bit here, oh no, I don't want to use the same color, come now. For this bit here, the gradient is positive, constant again because it's a straight line. You can see this line is a little bit steeper though than that line. So I would draw it a little bit bigger. Oh, this CC, that must be a D. Obviously, I'll change it now. So yeah, from C to D, you're going to have a flat line again, but the gradient here was positive, constant. But because of that negative sign there, your line will be a flat line here that is negative. Let's just fix that quickly. This would be our D and E. Now for this bit here, let's just use another color again. There my gradient is 0 again, so that means that from D to E, I'll have a flat line. Now what have I missed? A, no, they're all there. All right, so there we go, and that's what your line would look like. You can show little dotted lines. It's like the same as in the acceleration graphs. You can do little dotted lines there to show that they are linked. You don't have to, but it's nice if you just show that it's part of the same graph. So now we can go and answer the question. They say, during which time interval will the induced EMF be positive and not 0? So in these bits here, the EMF was 0, so we're looking for positive and not 0. So that would be from A to B. So the answer there would be A. All right, multiple choice, don't just guess them. Please remember they are important. 2 marks each. Then for 1.10, the name of the law used to determine the direction of the induced current in a conducting coil which experiences a changing magnetic flux. So the direction of the induced current, remember there's only 2 laws that are real laws, so please don't say left-hand rule or right-hand rule. It's only Faraday's law of electromagnetic induction or Lenz's law. The hand rules are not laws. So it would be Lenz's law. Lenz's law determined the direction. Lenz's law is responsible for that little negative there. Next. Here, the coil is rotating at a constant rate, and they say explain briefly why an EMF is induced in the coil. Again, your go-to answer, because when will there be an EMF? And Faraday's law helps you with this because EMF is directly proportional to the rate of change of magnetic flux. So if there's a change in magnetic flux, there will be an EMF. So you can say that. You can say there is a change in the magnetic flux or magnetic flux linkage, and therefore there will be an EMF induced. Now they say draw a sketch graph showing EMF against position for the coil, marking those positions. Now let's do that quickly. There are my video and another video. There are two videos that you can go and watch this step by step, but let's just do it again. Oops, we don't want a dotted line. Now, I always want to draw the flux graph first because that's the one that makes the most sense, because you can think about the lines passing through the coil and you have the mathematical equation for it as well. So I would always go and draw a little flux graph because you know that the EMF is going to be the negative gradient of the flux graph coming from Faraday's law of electromagnetic. Oh, can't spell. Induction again, because you know that EMF is directly proportional to the change in phi over change in time. But if we make it an equal, then we get the negative sign there. All right. So if we look at this one here, if it's in this position, there's my magnetic field, there's my normal there. So if you were going to do the maths, there's a 90-degree angle there. So cos 90 is 0. So flux is 0. But you can also see that no lines passes through that area. So we're going to start our flux graph at 0. When it's in this position, it's a maximum. Now, they didn't tell you whether it's positive or negative, but you go to the maximum there in this. So that would be so we're starting here at B. That would be Q. Then we're going to R when it's 0 again. I'm going a little bit faster because we've done this so many times now. S is a maximum again. So now it's on the other side. So it's negative maximum. And then at T, we're back at 0. Don't draw further than what the question is asking. They're just asking PQ, RST. Don't go and draw a wave for days. So, ooh. And there's my line. You won't get penalized for doing that. We're not artists, but you can try and draw it nicer than me. Then the EMF is the negative gradient. So here you can see the gradient is steep and it is positive. So I'm going to start on the negative side. Here the gradient at Q, I should have made it at Q. There you can see my diagram's a bit dodgy. But at Q there, it will be at 0. At R, my gradient is negative and maximum. So that means negative gradient will be then positive. And here I've got a 0 gradient again. Here I've got a positive gradient. So that means my value is going to be negative. And there we go. There is our curve. Once you have the dots and it's something rotating, it will be a sine or a cos graph. So if you know that it's something rotating, then go to sine and cos. But just remember, it's not always a sine and a cos graph. I just want to add something here. For transformers, you need to please remember that in a transformer, we have a primary coil that has a change in flux. So if I look at the primary coil flux, please remember that the change in flux in the primary coil is the same change in flux that the secondary coil is going to experience. So if you're going to draw these graphs for a primary and a secondary coil, the change in flux will be the same. So here you will have the same type of curve because they are experiencing the same change in flux. But now this flux is causing an EMF. This one has its own EMF and its own current that depends on the power source. But this one here, now this flux that this one is the change in flux that the secondary is experiencing is the reason why the secondary one will have an induced EMF. The primary doesn't have an induced EMF. The primary has an EMF that comes from the power source. So now the induced EMF is going to be the negative gradient of this one. So steep positive, I'm going to start at negative, and then you can draw your curve. Okay, so please just remember that this is the secondary. So the EMF here, or the current here, and this EMF will not look the same because the change in current is causing the change in flux. So they will be looking the same, and the voltage will be looking the same. But you need to remember that it's the induced EMF that will be the negative gradient, not the original EMF. Just keep that in mind. Ohm's law does not work for a transformer. Ohm's law says that the voltage and current is directly proportional in the same resistor, not in two different coils. Please remember this. It's only directly proportional in the same resistor. All right, and that's the end of my story for this chapter.